This is a special forum today. Each year, BYU chooses a faculty member to receive the Carl G. Mazur Distinguished Faculty Award, which recognizes accomplishments in scholarship and teaching and research, in citizenship. And then a few years ago, we decided to invite the recipient of this award to present one of the university forums. And David Long was the recipient of the award and will be giving our forum address as the distinguished recipient of the Distinguished Faculty Award this year. Dr. Long received his PhD in electrical engineering from the University of Southern California in Los Angeles in 1989. He had previously received both his Bachelor's of Science degree, his BS degree, and his Master's of Science degree from Brigham Young University. From 1983 to 1990, he worked at NASA Jet Propulsion Laboratory in Pasadena as a radar systems engineer. Since 1990, he's been a member of BYU's faculty in electrical and computer engineering, where he teaches upper division and graduate courses and conducts research in microwave remote sensing. Professor Long is a master mentor to students. He's mentored well over 100 graduates and undergraduate students during his time here at the university. Both the students and faculty greatly respect Professor Long, and he takes time to devote to he takes time for each to mentor and serve them and devote them individual attention to his students and his colleagues. We're told also that he keeps faculty meetings entertaining with his clever sense of humor. He's the director of BYU's Center for Remote Sensing and the head of the BYU Microwave Earth Remote Sensing Laboratory, and is a member of the NASA science team and the principal investigator on a number of NASA and NOAA-funded projects. He's published over 300 papers and received several awards from NASA for his work. Dr. Long's work on synthetic aperture radar use for archaeology was highlighted in the Discovery Channel documentary. He and his wife, Leanne, are the parents of 4 children, 3 of whom are currently students here at Brigham Young University. We're now very pleased to hear from Professor David Long.
Thank you. I'm Professor David Long. I'm an explorer, but in my explorations, I rarely leave my office. Instead, I study the world from BYU using remote sensing. Since beginning my engineering career at NASA's Jet Propulsion Laboratory, I've been privileged to work on many wonderful satellite remote sensing missions, including 3 scatterometers. A scatterometer is an instrument designed to measure wind over the ocean from space. My students and I helped design these missions. The NSCAT and SeaWinds missions operated perfectly for a year until their spacecraft failed. The QuickScat mission, which was launched in 1999, continues to operate 9 years later, well beyond its 3-year lifespan. QuickScat is about the size of a small car and orbits at a height of 700 kilometers. We use scatterometer data from these sensors to do research for NASA. We also develop new scatterometer technology and science application of the scatterometer data. Since coming to BYU, instead of launching spacecraft, I now get to help launch students. Over the 18 years I've been here, I have worked with many wonderful students at all levels who have been very long-suffering of my humor. Here are just a few of the students I've helped mentor in the launch into their careers. Today we're going to talk about how microwaves, icebergs, and global warming are connected. Along the way, I will talk about remote sensing and some of its applications. We will talk about climate and the connection between sea ice and ocean circulation. I hope to explain to you how greenhouse gases change the Earth's heat balance and to help you understand the science behind global warming. Recognizing the media controversy about global warming, I point out that my presentation reflects my own work and views and does not represent an official statement by the university or its sponsor. Okay, first, before we start, I have to correct a common misconception. There's no such thing as a rocket scientist. Really, we are engineers. Engineers are problem solvers. We create things. We use critical thinking, math, physics. We use engineering trade-offs to build and design new systems, including spacecraft and rockets. Solving the problems of space travel and remote sensing help engineers solve real-world problems on Earth. Modern technology such as computers, are spin-offs from the space program. When we spend money on the space program, it doesn't go into a black hole. No, we're spending the money here on Earth to better understand and solve problems on Earth, including climate. So next time you hear rocket science, think rocket engineering. My students and I conduct research in remote sensing. Remote sensing technology is one of the most important outcomes from the space program. Remote sensing means literally seeing from a distance. Here's Utah viewed from space. Most of you are already expert remote sensors. You use your eyes to see the world around you. Technology has given us powerful tools to improve our vision, binoculars, telescopes. Tools such as radar use microwave energy to give us a new view of the world. Remote sensing can help us see great distances from galaxies far, far away to the planets in our own solar system, such as Saturn, where the Cassini probe is currently orbiting, to closer planets such as Mars, where NASA has rovers exploring the surface. We also use satellites to study the Earth. As we zoom in closer to North America and Utah and toward BYU, we begin to see more and more detail and more familiar views, like those we see with our unaided vision. Remote sensing helps us place our local world into its larger global context. Okay, now I'm going to give you a short tutorial about radar to help you understand what follows. The key to remote sensing is knowing something about the electromagnetic spectrum. Light is a kind of an electromagnetic wave. Electromagnetic waves come in different wavelengths. The different colors of visible light have different wavelengths. Red light has the longest, while blue has the shortest wavelength. There are colors or wavelengths of electromagnetic waves that we cannot see with our eyes. For example, we can't see infrared waves. Instead, we feel infrared as heat. Microwaves are another kind of electromagnetic energy. Your microwave oven at home uses these waves to cook your food, but microwaves have other applications as well. Objects appear as different colors to our eyes because they reflect or absorb certain wavelengths. To illustrate how different wavelengths help us see things differently, consider these two pictures of me. One corresponds to red light and one to blue. When I was young, the freckles on my forehead were very visible. While these have faded as I've gotten older, you can still see them under the right color of light. Because they reflect blue light differently than the rest of my skin, they become more apparent under blue light. So we see that different wavelengths reveal different things. Remote sensing helps us exploit the full range of the electromagnetic spectrum, including microwaves. Radars operate at microwave and radio wavelengths. Remote sensing radars are like flash cameras. They illuminate or flash the scene with microwave signals and receive the signal that is reflected back from the surface or backscattered from that surface. Radars do not need other sources of light since they provide their own. And because radars operate at longer wavelengths than visible light, they see the world much differently than our ordinary eyes. Since microwaves penetrate clouds and can operate at night, and because the radar provides its own illumination, we can see through clouds and operate at night. If you had radars for eyes, this is what the world's land surface would look like. Note that the polar ice caps are very bright because ice reflects microwaves back to the radar so well. Deserts are dark because they absorb microwaves. Smooth, flat surfaces tend to appear dark because they reflect the signal away from the radar, while rough surfaces reflect some of the signal back toward the radar. So radar is kind of a measure of the texture of the surface. The amount of reflection is also related to what the surface is made of. Tropical rainforests are very bright because the leaves reflect well and because they look rough to the microwaves. Here's an example of how we can use satellite radar. Radar scatterometers were originally designed to measure winds over the ocean from space. And this is what I used to do when I worked for NASA. I designed satellite radar systems. This animation shows a scatterometer measured winds blowing around a hurricane off the East Coast. In this picture, colors show the wind speed while the lines are the wind direction. Red and yellow represents high wind speeds, while blue shows calmer winds. Scatterometers measure wind by measuring the small ocean waves on the surface called cat's paws. Cat's paws are small waves that you see when a gust of wind blows over the surface of the water and kind of roughens it. From roughness measurements made by the scatterometer, the wind speed and direction can be estimated. The scatterometer also collects data over land. My engineering students and I have developed computer processing techniques to make radar pictures from the scatterometer data. These pictures have proven remarkably useful in studying the Earth. Now, modern weather satellites carry very sophisticated remote sensing equipment to monitor hurricanes. These help us understand how these weather systems work and to predict their movement and extent. While the visible light movie of hurricane cloud tops is very impressive, the real destruction is actually occurring at the surface, where high winds and rain whip up huge ocean waves, drive storm surges, and destroy buildings and trees. Since 3/4 of the Earth's surface is covered by ocean, to predict the weather, we need ocean wind measurements at the ocean's surface. Unlike other satellite sensors, radar scatterometer measures the wind at the surface. So the scatterometer missions fulfill this need and result in improved weather and hurricane forecasting. Conventional scatterometer measures are made on a 25-kilometer grid. However, here at BYU, we have been developing advanced techniques to measure wind speeds at even higher resolutions so we can see more detail. The colors shown in this are again wind speed, with the purple being the very strongest winds. Note the hurricane eye near the coast. These higher resolution images are improving forecasters' ability to predict and track hurricanes. Our data is used by the National Hurricane Center for hurricane tracking and prediction. Now here's an example of how scatterometer data is useful for studying tropical rainforests and changes in it. This radar image shows part of South America. The light area is tropical rainforest, jungle, while the gray area is savanna and woodlands. The Amazon River is visible as a branching set of black lines. Comparing radar data taken in 1978 and 1996, it is clear that extensive changes occurred. In this image, yellow marks mild changes, while pink indicates areas of significant change. The colored regions are associated with reservoir construction, road building, and human settlement. Significant fractions of inland and coastal rainforests have disappeared in the 2-decade period shown here, and this trend has continued to accelerate. This is only one example of how humans are rapidly changing land use on very large scales. BYU has helped pioneer the use of scatterometer data for other applications like studying snow and ice. Here's the very first QuickScat image of Antarctica that I generated right after it was launched in 1999. The South Pole is the center of Antarctica. Antarctica is very bright due to radar reflections from the thick layer of snow which covers the continent. Surrounding Antarctica is a band of sea ice. When I first looked at this image, I discovered what looked like an extra island, a huge iceberg known as B10A in the Drake Passage between South America and Antarctica. This iceberg was formed when the end of a huge glacier broke off. The technical term for an iceberg being formed like this is calving. I reported this find to the National Ice Center, which tracks such things. They were surprised to learn that the iceberg was in a shipping lane and issued an international iceberg alert. BYU got a lot of media attention over this discovery. The National Ice Center has been tracking B10A for months, but had lost track of it due to cloud cover and winter darkness. Here on the left is a false color photograph of B10A. This iceberg is huge, 60 by 25 miles in size, bigger than Utah Valley and nearly 1,000 feet thick. The little inset shows what looks like dandruff, little white spots in the water surrounding the iceberg. These are actually icebergs a half-mile in size, larger than the iceberg that sucked the Titanic. Radar allows us to easily track B10A in darkness and through clouds. In this animated sequence of daily radar images, we can watch the dance of the icebergs as B10A and its equally large sister A22B move in response to wind and ocean currents. You can also see the rapidly moving sea ice and the flicker of wind-induced roughness of the ocean. The size of B10A is actually not unusual. Antarctic icebergs are enormous. Here's another one, A22A, in a picture taken from the International Space Station by astronauts in 2007. This little iceberg is only 12 by 25 miles in size, while the largest recorded iceberg was 180 miles long by 60 miles wide. We're still tracking pieces of this baby. BYU has been providing iceberg positions to the space station astronauts who enjoy photographing them. Just recently, I got another email from Mission Control asking for information about a particular iceberg that the astronauts had photographed. In this photograph of an Antarctic iceberg from a ship, we can see how thick an iceberg can be. This iceberg rises 60 feet into the air, and since 9/10 of the iceberg is actually underwater, this means that it extends 600 feet deep. Now, our radar data is being operationally used by iceberg trackers at the National Ice Center. BYU has become a primary source of iceberg tracking information. Twice a week, we provide updated tracking information, which is broadcast worldwide for ship warnings. In many cases, BYU is the only source of an iceberg's location, which is ironic since we don't see very many icebergs here in Utah. In this animation, the circles show locations of icebergs that we tracked over a one-year period. Note the dynamic motion of the icebergs and the sea ice. Our success in using scatterometer data to track icebergs has enabled us to address some important scientific questions. Okay, so what does all this background have to do with climate change and global warming? Remote sensing gives us information that we can use to investigate climate change. So I'm going to give you several examples and applications of how we can do this. Based on a database that's maintained at the National Ice Center, in 2001, it appeared that the number of icebergs, here plotted in blue, was increasing. Someone suggested that this could be evidence of global warming. To test this, my students and I went back into the historical scatterometer data archive and looked at the icebergs over the last 30 years. This data is plotted in other colors. We determined that some of the apparent increase in the iceberg count is actually due to improved tracking technology. For example, the Ice Center undercounted the icebergs before 1990. In addition, there were major iceberg formation events, calvings, that occurred in 1996 and 1999. However, these were from ice shelves that were expected to calve soon. These ice shelves produce massive icebergs about every 50 to 60 years, and the last time they did so was about 50 years ago. Thus, these events are well within the expected range. And so in a published paper, we concluded that the increased iceberg count was not related to global warming. No, this result doesn't mean that global warming is not occurring, only that the iceberg count couldn't be used as an evidence. Several recent ice shelf breakups have, in fact, been traced to warming conditions. Let's look at another application. Radar is particularly useful for monitoring melting in Greenland. This is an area considered a bellwether of climate change. Greenland is an island covered with snow to a depth of over a mile. The weight of this mountain of snow is so great that it has depressed the center of the island to below sea level. The snow at the center of Greenland is piled high enough that it never melts, even in summer. As the snow piles up, it flows to the sides in great glaciers and becomes thinner at the edges. Along these lower edges, melting occurs in the summer. At the top, it never melts. Lower down, meltwater percolates into the snow and refreezes. Further down, there's enough melt to actually result in water-saturated snow, something we call slush, which we're all familiar with of late. Below this, the snow melts off every year, and all that is left is ice. The locations of these melting zones are very, very sensitive to climate conditions. Thus, monitoring the melt can help us understand if the climate is changing. Because microwave signals are so sensitive to melt and liquid water, they are a very good tool for this. Here are a series of false color radar images of Greenland over the last 3 decades. The images show the difference between the radar backscatter for the year and the 30-year average backscatter. The dark colors along the periphery in 1978 and 1996 are due to less melt during these years than at present, while the lighter colors in 2000 and 2008 suggest that more melting is occurring now. This is consistent with a warming pattern in Greenland and is very strong evidence of global climate change. As if to prove climate is complex, at the top of Greenland, the color is darker in 2008 than it was in 1996. This indicates that snow accumulation is now greater than it was then, 30 years ago. This observation is also consistent with global warming, since warmer weather causes more evaporation, which leads to more precipitation and snow, at least in some locations. So, we have more melting and more snow accumulation. Which is winning? More melt or more accumulation? Careful analysis of the data shows that increased melting is winning. Greenland is warming, and as it warms, it is melting, releasing the water that has stored as ice into the ocean and raising sea level. The rise in sea level is small so far, but could accelerate as the flow of glacial ice is lubricated by melting water. Okay, so let's talk more generally about climate. Climate is weather averaged over a long time, many years. Climate is why we think of southern Utah as being hot and dry in the summer. On average it is, even if some days are cooler and wetter than others. Scientists know that climate is not a constant. It is always changing. It varies in response to changes in energy from the sun, the Earth's orbit, dust from volcanoes, and human activities. Some of these changes are predictable, like the Earth's orbit about the sun. Others occur more randomly, like volcanic eruptions. Once there were so few humans that we had very little impact on our environment. The Earth may seem huge, but it is a closed system. There are now so many of us, and our technology is so powerful and pervasive that our collective activities are impacting the environment, including climate. This is what we'll now consider. First, in talking about climate, we have to remember that climate is very complicated. It involves long-term averages of many things. These things interact in complicated ways that sometimes reinforce and sometimes cancel each other in a process that scientists call and engineers call feedback. Frankly, we don't completely understand all the aspects of these feedbacks. However, we do understand the basics. One factor is the connection of ocean circulation with the formation of sea ice. Sea ice formation is one of the causes and drivers of ocean circulation. Cold winds from the poles blow over the ocean, causing ice to form. However, salty seawater does not freeze well. As the ice forms, the salt is squeezed out of the ice and is concentrated into cold, dense, salty water that sinks to the bottom of the ocean. This cold water flows along the bottom from the polar regions to where it rises to the surface and is warmed. Meanwhile, the sinking water is replaced by warmer water drawn from the equator, resulting in global circulation of warm and cool water. This circulation is what keeps the equator from being too hot and the poles from being too cold. It is the key to our current climate. If it were to stop, the Earth would quickly become very uncomfortable. Thus, sea ice plays an important role in climate. Remote sensing of sea ice helps us track climate health. BYU engineering students created the computer code used to make these daily images in this animation of the Earth's southern hemisphere, which shows this region over part of a year. These images were processed on BYU's Mary Lou supercomputer, and the ocean flicker masked off. Remember the iceberg movies? The Antarctic continent is covered with a nearly 2-mile thick ice sheet. Around it is sea ice, which is typically about 2 meters thick during the winter. During the summer, this sea ice melts and almost completely disappears. In winter, the sea ice grows back rapidly, creating the cold water that drives ocean circulation. Once formed, sea ice tends to insulate the ocean from the cold and reduces the input to the circulation. Sea ice in the Arctic is much thicker and behaves somewhat differently than Antarctic ice, since there's a permanent floating ice cap. In summer, only part of the sea ice melts. Summer melting causes ice to appear darker to the radar. We could observe the passage of warm fronts over the poles and monitor tundra melting in Canada and Siberia as swirling patterns of light and dark in this animation. As the summer progresses, the polar ice cap shrinks as it melts. In the winter, the ice pack grows, both larger and thicker. Now, you may have heard stories about the shrinking Arctic ice cap in the news. Our data confirms over the last decade that the size of the summer ice pack in the Arctic is in fact shrinking and that the cap is thinning. This is consistent with global warming. Paradoxically, we've also observed that sea ice extent during the winter has also grown. I want to note that our radar images are operationally used by the Navy and international agencies to aid in ship routing as well as in monitoring climate. Okay, so let's talk more about global warming. Almost everyone has heard of greenhouse gases and the connection that carbon dioxide, or CO2, has with global warming. This plot shows the concentration of CO2 in the atmosphere over the last 400,000 years. This data is derived from tree rings, seashells and ocean deposits, and ice cores from Greenland and Antarctica. Notice the large fluctuations. These fluctuations are the result of natural cycling due to variations in the sun's output and the Earth's orbit with some volcanic events. However, in the last 100 years, the amount of CO2 in the atmosphere has nearly doubled due to human activity since the Industrial Revolution. I want to point out that CO2 is not the only greenhouse gas that's been increasing due to man's activities. Other greenhouse gases, such as methane, natural gas, usually from cow digestion or rice paddies, and nitrous oxide from pollution, also show similar dramatic increases. The concern here is that the rapid increase in greenhouse gases is causing global warming, and that the rapid warming will leave little time for plants and animals and human society to adapt. So, is the Earth really warming? This seems like a simple question, but it is complicated since we only have had accurate thermometers for the past 200 years or so, and they are not evenly spread. This results in uncertainty in the precise values for global temperature. So we use measurement error bars to show the possible range of a value. This plot shows the yearly difference in global temperature from the average over the last 150 years. The dots show individual yearly average temperatures. They are smooth to form the blue line. The gray band indicates the uncertainty error bars for the smooth line. Note that this data shows that the Earth has warmed about 1 degree Celsius since the beginning of the Industrial Revolution in the 1800s. So what's the big deal about a degree or two of warming? Well, even small changes affect ice melting and formation. And because of feedback effects, small changes can become larger changes, resulting in even more change. Further, rapid change is difficult to adapt to. Will warming continue based on current trends? Yes. We can extrapolate the trend by fitting a curve to the data. The answer depends on how the fit is done. Much of the controversy over global warming revolves around the rate of warming, how warm it will get, and what we can do to mitigate it. But in any case, it is clear that temperature is going to increase. Let's delve into the science of why. Unlike the federal government, the Earth has to live within its budget, its energy budget. Energy comes to the Earth from the sun, primarily in the form of visible light. This solar energy is converted to heat upon hitting the Earth. The temperature of the Earth is controlled by how much of this heat is radiated back into space as infrared energy. Clouds reflect some of the light, so they keep the Earth cool by reflecting sunlight back into space. However, clouds also trap heat beneath them. This is why cloudy winter nights are, on average, warmer than clear winter nights. Greenhouse gases, on the other hand, both let the light in and trap the heat, which is why greenhouse gases cause warming. Ice at the poles also reflects light from the sun back into space, which helps the poles remain cold. However, when sea ice melts, the dark ocean absorbs the light and warms. This causes more melting, a positive feedback effect. Warming melts the ice, which leads to more warming, which leads to more ice melting, which leads to more warming, etc. All right, now this is probably a bit too ambitious for a general audience, but I want to explain how greenhouse gases really work. This is a simplified description. Let's return to the electromagnetic spectrum we studied earlier. We are concerned with the visible light and infrared wavelength portion of the spectrum. As I said, energy comes to the Earth from the sun, primarily in the form of visible light. The height of the blue curve shows the amount of energy from the sun at each wavelength. We call this the solar spectrum. The height of the red curve shows the Earth radiated infrared spectrum, the infrared energy that is radiated into space at each wavelength. At the surface, the light from the sun is converted to heat. The surface radiates heat upward as infrared energy. However, gases in the atmosphere do not let all the wavelengths through, all the infrared wavelengths through. Gases absorb some of the infrared energy, heating the atmosphere. The important idea here is that each gas absorbs at different wavelengths. Oxygen and nitrogen do not have much effect. On the other hand, water vapor has a huge effect. The blue curve shows at which wavelength it absorbs. Water vapor dominates the absorption spectrum over a wide range of wavelengths. Water vapor is highly variable, which is one reason why climate models have so much uncertainty. Here is the important part. Greenhouse gases absorb at different wavelengths, and these wavelengths are in the holes of the water vapor spectrum. This means that greenhouse gases increase the amount of heat that the atmosphere absorbs. The Earth warms as a result. Thus, the temperature of the Earth is very sensitive to the concentration of these greenhouse gases. The more gas, the more heating. In addition, more heat also causes increased evaporation, which results in more water vapor, which reinforces the warming, another positive feedback effect. However, as if to complicate matters, water vapor also causes more clouds, which reflect the sunlight back into space before it turns to heat. This causes a cooling effect and is a negative feedback effect. So determining how much warming is really occurring can be very complicated. So to understand what happens, scientists have developed and tested mathematical models. These models are sophisticated computer programs designed to analyze and predict global climate. Because the climate is complicated, the models are complicated and inherently incomplete. They are not perfect, and there is uncertainty in the results. However, they do include everything we know and understand about climate. Scientists have tested the models by predicting past climate conditions. The models do a good job of matching the climate history, so we believe the models, at least to a degree. The models are then used to analyze current weather and climate conditions. These plots show the temperature change versus time for the globe in various regions. The black lines show the observations. The bands show the range of uncertainties for the outputs of the models. If only natural cycles are included in the models, the blue bands result. When human effects like measured greenhouse gas emission and land use change are included, the models correctly reproduce the global warming that we've observed over the last 50 years. This is the reason why we can conclude that it is very unlikely that 20th century warming can be explained only by natural causes. Okay, so here are some very dry but hopefully precise scientific statements. Recent warming is consistent with the scientific understanding of how climate should respond to a rapid increase in greenhouse gases like the one that has occurred over the last century. Further, the warming we have observed is inconsistent with our scientific understanding of how the climate should respond when only natural measured forcing factors such as variability in the solar output and the Earth's orbit and volcanic activity are included. Our confidence in these models is increased by the fact that the models produce a geographic pattern of temperature change that is similar to that which we've observed in recent decades. This spatial pattern, which has greater warming at high latitudes, differs from the most important patterns of natural climate change variability. So what's the future? Well, it does not appear that we're going to stop producing CO2 or other greenhouse gases. We like our modern conveniences too much. In fact, CO2 release is actually increasing. This will result in increased warming. Further, it takes a long time for CO2 to be removed from the atmosphere, estimated to be 50 to 100 years. So even if human CO2 release is suddenly stopped, warming will continue for a while. So far, oceans and soil have been absorbing much of the human-generated CO2 from the atmosphere. There are concerns and some evidence that these CO2 sinks are becoming saturated or filled. The ocean, which has been absorbing a lot of human-released CO2, is becoming more acidic as a result, which is adversely impacting sea life. So is global warming all bad? Well, it all depends on where you live, since some areas will be more affected than others. Some may even benefit. However, ocean circulation changes will result in greater variability in weather. We don't think that ocean circulation will stop, though it has in the distant past. Increasing temperatures will result in further melting of the polar ice caps, resulting in rising sea levels and coastal flooding. If we are lucky, the sea level rise will be small. However, if warming is large enough to cause dramatic increases in the melting of the Greenland and Antarctic ice sheets, the result could be dramatic rises in sea level. Fortunately, the result is now considered to be unlikely, at least in the next half century, but it remains a concern. We will see changes in precipitation patterns in some areas, with some areas getting more and some areas getting less precipitation. There will be more droughts. Water supplies will be less certain due to less predictable and more variable rain. This may have an impact on mankind since the breadbaskets of the world are thought to generally become drier, placing stress on human populations. The news is not all bad, however. Increased CO2 can actually aid crop growth, at least to a point, and if there's enough water. I note that Utah is thought to become warmer, which will result in less snow warmer in the winter, which will result in less accumulation of snow in the winter and less storage of the mountains. Even if the amount of precipitation in Utah remains the same, new long-term storage capability may be needed. So what's the bottom line here? First, the climate is complex. Second, global warming is real. While there are uncertainties, natural cycles cannot account for the observed warming. Human activity is contributing to the warming. Fourth, the consequences of warming will be generally adverse and will be with us for a while. It is truly unfortunate that climate concerns have become so politicized over the last few years. This is an issue that should transcend politics. We're all in this together, so we need to work together. Now, as various groups consider ways to mitigate the effects of global warming, I want to leave you with this thought. Even with the doubt and uncertainty about climate change, things that reduce greenhouse gases generally have the effect of protecting and preserving the environment, which is a good end in and of itself. By wise and efficient resource use, we can save both our money and the planet. Now, it has been suggested that it is, by some, that it is arrogance to think that humans can adversely affect the Earth. However, I think the reverse is true. My work in remote sensing has helped me realize that we are affecting our planet. Every action has a reaction. Let us choose our actions wisely. I believe that God expects us to be good stewards of our world. It is our responsibility to pass on a viable world to our grandchildren. You know, it seems to me that God does not always protect us from the consequences of the foolish actions in our personal lives. Why would we think that He would protect us from our environmental foolishness? Finally, I present this radar remote sensing of the BYU campus taken just this last week. Although not as colorful as a conventional photograph, this image would look the same day or night. Well, maybe except for the student cars in the parking lot, and during finals week, probably even then. I want you to know that I believe in a real and personal God, that He lives and cares about us. May we always follow His guidance and enjoy His blessings. In the name of Jesus Christ, amen.